So you guys, this is the IB syllabus for 5.2. Take a look at the essential idea for a second. One of the earliest uses of electricity was to produce light and heat. So we've been studying static electricity. We're now going to move into current electricity. And one of the big uses of current electricity is lights and making heat. And now we can do a lot of other things with it as well, but that's one of the earliest uses for it. And it certainly impacts us. These are the things we're going to be learning about, these understandings. And then you'll see also that there's quite a few equations that we'll deal with. We will cover a few of these today, and you'll see we'll cover a fair amount of this stuff today. So, but we're going to start off with a little bit of history between these two guys, Luigi Galvani and Alessandro Volta. You don't need to know this history for the IB exam, but it's just kind of something to get you started. These guys were professors and scientists in Italy back in the late 1700s. And Luigi Galvani did an incredible thing. He took frogs' legs. So they were like dead, right? They weren't attached to frogs anymore. They were just legs. And he would stick two pieces of metal, little probes, into the frog's legs, and they would start to twitch. And he was like, whoa, this is so cool. I have just discovered the essence of life. There's something that I'm tapping into with these metal probes that is like the life force. Here I have a dead, inanimate object, and when I probe it just right, it starts to move. It starts to come back to life. Haha. So he was kind of like Dr. Frankenstein. He was super excited. Now, Alessandro Volta, see, these guys were at competitive universities. Galvani was at the University of Bologna. Volta was at the University of Pavia. These were like arch rivals, all right? If you follow college basketball, it's kind of like Duke and Carolina. If you know, whatever, it's like serious rivals. So Galvani's like, I've discovered the source of life. Look, I can make dead legs move again. Volta's like, I don't think so. I don't think that's what you've done. I think it has to do with the metal that you're inserting into the frog's legs. And somehow there's some sort of electric current or something happening that's bringing it back to life. So he sets out to try to prove Galvani wrong. But it's hard because back in late 1700s, they didn't have ways of generating a lot of electricity. Volta couldn't measure that there was definitely electricity flowing. So it's hard to prove. But he sets out to try to do it. In the end, Volta kind of wins out that yes, Galvani did not discover the essence of life. What he was doing was by sticking two metal probes into the frog's legs, he was generating an electric current through the muscle fibers, which is causing the leg to twitch. And Volta continued to work with that, and in time he came up with this kind of an invention. These are pictures of batteries, the invention of the battery, and Volta kind of worked on that a lot. And what he discovered is if he took two different kinds of metal and made these little kind of sandwiches with two different kinds of metal, and especially if he bathed it in some sort of conducting fluid, that he could get electricity to flow. Now remember, with static electricity, all we could do was charge something up and make a spark. So it was like a big discharge very quickly. What Volta was starting to do was make electricity that would flow more continuously over a period of time, and that was useful. We can start doing things with it. And this was in the late 1700s. These are batteries. Each one of these little sandwiches is called a cell. Put them together, it's called a battery. This is another picture of an early battery. They were much larger than they are today when he first invented them, but it was kind of cool. This was a major step. And yeah, these are like sandwiches of two different kinds of metal. And the key here is that they had to use two different, and this one I think he used copper and zinc, it looks like, and two different kinds of metal when sandwiched together and with appropriate fluids can cause electricity to flow. And in some ways that's a little bit what our batteries do today. You have metals in there and you have things that will oxidize them and cause electrons to flow. Okay? So with current electricity, what we're going to need are circuits. An electric circuit is just a pathway, a closed loop that electricity can flow through. You have to have a loop. You have to have a pathway from an area of high voltage to an area of lower voltage in order to get electric current to happen. Okay? So that's what a circuit is. You're gonna need to be able to draw circuits and recognize circuit diagrams. Remember in your data booklet that there is a whole page of symbols that IB will use in their circuit diagrams. Okay? Okay, here's three little pictures of a battery and a wire and a light bulb. Notice that when you have a battery that looks like this, you have the little bulb that sticks out, that's the positive end, and the bottom of the battery is the negative end, okay? So those are the two terminals that are at different voltages, higher and lower voltages. On the left here in picture A, will that light bulb light up? Why not? It will not? Why not? you don't have a complete circuit, right? You haven't completed a path from the high voltage to the low voltage. How about in picture B? No. Absolutely not. But look, here is a loop, right? We've created some sort of a loop here, but what's wrong?
It's not closed.
It's not, and it's not connecting the negative and the positive. Great. And then C?
Yes.
Absolutely. We finally made light. Woohoo! Because the electricity can now flow into the light bulb, through the filament, down the wire, and back to the negative terminal. We have a circuit. We have a complete loop here. Okay? Great. So that's what electric circuits are, just a closed. Okay, so here is a circuit, like a picture of a circuit with a battery and a light bulb, and then the diagram of it. So we'll usually draw diagrams to simplify things. Notice that wires are just lines. We generally will assume that wires have zero resistance and don't affect our circuit. Okay. This little symbol down here is a cell. Okay, and we'll draw a cell with a long line and a short line, and if we have multiple cells put together, we'll call that a battery. Okay. The way we do it is the end with the long line is the positive terminal. The end with the short line is the negative terminal, right? So we've got positive and negative. Okay, so that's the symbol for a battery. Current, we will always draw electric current traveling from positive to negative, which is a little bit weird because now we know the thing that's moving are electrons, right? And the electrons will be repelled from the negative and attracted to the positive. So the electrons actually go the other way, but we draw current. It's called conventional current, and we always draw it from positive to negative. And then anything that has resistance that will do something with the electricity, make light, make heat, something like that, that will be drawn as like a rectangle, or sometimes you'll have a symbol like this that's with wires going through it. That's a device. And all these symbols are in your data booklet for what they mean, what they stand for. Okay? So electric current is represented with the symbol I. So in equations, when you see the letter I, that means electric current. All right? And it's basically the rate of flow of electric charge. Okay? It's how many coulombs of charge are flowing past a point every second. Though we technically don't define current that way. It's weird because it's hard to see little electrons flowing. So the actual definition of what an amp of current is defined using force rather than the rate of flow of charge. But conceptually, think of it as the rate at which charge is flowing. It's measured in amps, all right? And the amp is named after that great physicist Andre Ampere. And an amp, 1 amp of current is equal to a coulomb of charge every second. And that is a very large unit of charge. We will usually be dealing in milliamps or microamps or something like that, because an amp or 2 amps or 3 amps is a huge amount of electric current. Okay, and when we're talking about electric circuits, we're going to try to measure current, and we're going to use a device. What are we going to call that device to measure electric current? Yeah, well, what do we use to measure temperature? Thermometer. Great. And what do we use to measure air pressure? Barometer. Great. Right? What do you use to measure speed in your car? Speedometer. Right? Good. So what are we going to use to measure current?
Electrometer. Ampometer.
Ampometer. Good. An ampometer. We call it an ammeter, though. An ammeter, is the tool we will use. And in order to measure current, you got to make sure that you connect the ammeter correctly, and then that means you have to connect it in series. At this point, you don't know what that word means. We'll talk about it in a little bit. Just write it down and remember it. That ammeters must be in series in order for them to function properly. You don't need to memorize these numbers, but here are just some ideas of what different amperages can do to you. Again, just to give you an idea that the amp is a large amount of current, because very small amounts of current you can feel and start to be painful and things like that. Try this one out, you guys. Take a look at it. This is an IB question. See what you can do. Okay, if you're listening at home, hit pause. Here's your answer. You ready? Should we tell them?
It's B.
It's B. It is B. B is the correct answer. Okay. Potential difference, voltage. This is a concept we talked about quite a bit last unit. We'll cover it again here. It's represented by the letter V in your equations. And you can think of potential difference in circuits as kind of being the driving force, the pushing force. How much energy is pushing the charge through the circuit is kind of a way of imagining it. Technically, it's the amount of work per unit charge required to move the charges around the circuit. Okay, that's what voltage is. So remember, it's joules per coulomb. It's the amount of work per unit charge in moving the charges around the circuit. It's also how much energy those charges can do. Okay? It's measured in volts. So this is one of those few things where the symbol in the equations is the same symbol as the unit. Okay? So V for in the equations and V for the units. And a volt is a joule per coulomb. I think that's helpful to know. Remember, joules are a measurement of energy. Coulombs are a measurement of charge. So a volt tells you how much energy the charges have when they're moving through this, how much work they can do. And it kind of, like I said, is kind of like the driving force behind the circuit. We measure voltage with a voltmeter, okay? And voltmeters have to be hooked up in parallel in a circuit rather than in series. So those are two terms that we've talked about and haven't defined. I'll show you what those mean here in just a second. Okay, so here's a real simple circuit. I've got a battery, I've got some wires, I've got a device. This is the positive terminal, this is the negative terminal, so I would draw current as flowing that direction, right? Great. Now, if I want to measure the current, what's the tool called? An ammeter. Great. And in order to measure the current in this circuit, I have to place the ammeter within the circuit so current will flow through it. That's what it means to be in series. So I would place the ammeter, for example, right there. And notice that there's only one path that the current can flow, and that path is through the ammeter. So my ammeter is in series. It'll tell me how much current's flowing through the circuit. Right? If I want to measure voltage, now voltage, again, is like energy, how much energy the charges have. And the voltage only changes if something does work, if something uses that electricity and does something. So this device will change the voltage. And if I want to measure how much voltage that device uses, I have to take my voltmeter and I have to place it around the device. This is what it means to be placed in parallel. So that now there's a secondary path, there's two paths, that's what parallel means in the circuitry. And I can measure, my device is measuring the voltage here and the voltage here and showing me the difference, the potential difference, okay? It just so happens if, let's say, this is a 9-volt battery, it's providing 9 volts to my circuit, and I only have one device, it should read 9 volts, okay? Because 9 volts have been provided, 9 volts get used, and everything works nicely that way. If I take my voltmeter over here, what do you think it'll read?
Yeah.
What, exactly, and why 0? Right, no energy's been used. So the difference in potential from this location to this location is 0. Nothing's changed.
So in that, is it saying that the device is using 9 volts, therefore there's potential difference in 9 volts?
Yes, this bottom one, yes, exactly. Now, where mistakes get made is if I take my voltmeter and do this, connect it within the circuit, my circuit fails. It ruins the circuit, doesn't work. Or if I take my ammeter and I connect it like this, my circuit fails. Okay, so just be aware that when you're connecting these things, which we'll do later today, you have to connect them right or else everything gets messed up. So there's this thing called Ohm's law. It's a pretty simple little equation. It's not technically really a law in the physics. It's more of like a definition of resistance. But this German scientist named Georg Ohm, he did some research and he discovered this relationship, R equals V over I. R stands for resistance. And so Ohm's law is not really a law, it's kind of a definition of resistance. And what he really discovered is that when you keep the temperature constant of a conductor, particularly a metal conductor, the current through that conductor will be proportional to the voltage. So really kind of, what Ohm's law says is that current is proportional to voltage if the temperature is kept constant. And that means the reason that's important is because what he discovered is that if the resistance is kept constant, then more voltage gives me more current. Double the voltage, I'll get twice the current. Triple the voltage, I'll get 3 times the current. Okay. The thing that he discovered though is that temperature can affect resistance, right? So that's if I change the temperature of a wire or a metallic conductor, its resistance changes, and then Ohm's law doesn't hold true anymore. Okay. And generally speaking, the hotter something is, the more resistance it has. Hotter it is, the more resistance it has. So imagine this is a wire, and each of those little dots is an atom in the wire. There's a lot more than that, but imagine those are atoms in the wire. They're relatively stationary, right? They're held in place because it's a solid. When you connect this wire to a source of voltage, what happens is an electric field is produced in your wire, and that causes the electrons to feel a force, and they want to accelerate, okay? So the electrons start to accelerate, and let's imagine, bless you, let's imagine that my electric field in my wire, E, let's see, I'll do that here, my electric field is in this direction. Remember, electric field is the direction that positive charges would feel a force, so my electrons will actually be accelerated in the other direction. And so they all want to start flowing to the right. But these atoms are in the way. They're stationary, and they're kind of like little, you know that game with all the nails, and you drop like a coin at the top or something at the top, and it goes bing, 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 and it bounces? Yeah, the Plinko or whatever. It's kind of like a Plinko machine where the electrons, they start to accelerate. Here's my little electron. And it's going, 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 and then poof, it collides with something. And it's like, ah. And then it collides with another one. Ah. And so it's constantly like colliding as it's trying to move through the wire. Every collision is an inelastic collision. So every collision gives a little bit of energy to each atom that it bumps into, and that causes them to start to vibrate, and that causes the wire to heat up, okay? So as current flows through, it tends to cause things to warm up. The wire starts to heat up, but then another thing happens. There's my little heat, right? Imagine now that when these atoms are hotter, they're vibrating more rapidly, and that means they, in effect, appear larger. So since these little, not the electrons, these atoms, since these little atoms are now vibrating at a higher temperature, they appear like larger targets, and that's why resistance goes up, generally speaking, when temperature goes up, right?
Exponential, that just get.
Now, this idea of resistance it's a fact of what goes on with electricity, and every conductor has some amount of resistance, okay? Except for, we do have these things called superconductors, where when you cool things down near absolute zero, then they have zero resistance, and it's super crazy. We're going to kind of not pay attention to that right now. And just if you're thinking about a wire conducting electricity, there's three things that will determine how much resistance it has. What do you think those three things are? Okay. So three factors that affect resistance. This is the equation. It's in your data booklet. So R is resistance. It's equal to rho times L divided by A.
Rho.
Yeah, and rho, the Greek letter rho, basically is a property of the given material. It's how resistive that material is. It's called the resistivity, and it's a number that's specific to the material. So copper has a certain resistivity, silver has a different one, lead has a different one, okay? Or you'll be solving for it or something like that. L is the length, so a longer wire or a longer conductor will have more resistance, and A is the cross-sectional area. For IB, you can almost always assume that wires are circular in cross-section, right? That you're going to have a circular cross-section. I don't think that we'll usually deal with like rectangular or square cross-sectional wires. It's pretty unusual. The unit for resistance is the ohm, okay? And that is basically the amount of resistance that will allow 1 amp to flow when there's 1 volt of potential difference across it, okay? And what Ohm's law says, you can kind of, bless you, you can kind of reorganize Ohm's law to say I equals V over R, right? So in a circuit, I can do two things to change the current. I can either change the voltage or I can change the resistance, or both, and those will affect how much current flows through a circuit. So current can be controlled from a given voltage by changing the resistance. That's basically how light dimmer switches work. So if you're listening at home, feel free to mess with this question if you want. The answer is
D.
D is the answer. D is the answer. But something I want you to actually pay attention to, and all you guys wanted to look at that, is so when a device, when its resistance doesn't change, this graph will be linear, and we will say the device is ohmic. Ohmic. It obeys Ohm's law. Okay? But most devices aren't ohmic. Most devices will heat up and their resistance will change. And then you'll get something like this, where the curve starts to taper off a little bit. And then we would say it's non-ohmic. It's not obeying Ohm's law because that ratio of voltage to current is not staying constant. Okay? Its resistance is changing. A classic example of a non-ohmic device that IB wants you to know about is a light bulb, a traditional incandescent light bulb. Okay? The old school light bulbs that we used to use a lot and that we're moving away from. Basically, how do they work? Excellent. You basically get a little piece of wire in there that gets so hot it glows and makes light. Okay? Now, remember we told you when things heat up, the resistance changes. These bulbs are not ohmic. They don't follow Ohm's law because they get hot and their resistance changes. By the way, they're really terribly inefficient at making light because they make a lot of heat. They're really good at making heat. But they do make light as well, but they're inefficient. They lose a lot of energy in the form of heat. That's why we're moving towards LEDs and compact fluorescents and other things that produce a light with a lot less energy. So power is the last thing we need to talk about. It's represented by the letter P, and it's the same thing that we talked about last year. So what is power? Joules per second. So it's work. It's how fast work is being done or how fast energy is being used. Great. And with electricity, that still holds true. Power is still the rate at which work is being done or the rate at which energy is being used. What's the unit for power? The watt. Great. It's measured in watts, which are joules per second. Okay, joules per second. And so in electricity, the way we measure power is basically current times voltage. Current times voltage. And if you look at the units, it makes some sense. Current is coulombs per second. Voltage is joules per coulomb. So if I multiply those two, the coulombs cancel out, and I'm left with joules per second, which is watts. Okay. So if I have a circuit, take the voltage times the current, I'll get the power. So if P equals IV, and Ohm's law told us that R is equal to V over I, right? Well, I can combine these two equations and get two more. So it turns out there's three equations for power. Okay, there's three equations for power by combining those two, and here's what they look like. And they're all in your data booklet. So it just depends on what you know and what you're trying to find out in terms of power. Do you know voltage and current? Do you know current and resistance? Or do you know voltage and resistance? So here's an actual IB question. I would say this is actually a relatively easy IB question. That's why it's only maybe worth 2 points. But throw in the equations. I bet you could do this in probably about 48 seconds. For the first one? P equals I times V. Great. So what do we get? 0.5 times 12, 6 watts. Great. And the second one, and technically for sig figs, what would we say? 6.0 watts. Good. And then the second one? Oh, you could. P equals I squared R, but what's an easier one? R equals V over I. Is that right? 12 over 0.5 gives me 24 ohms. Great. 2 points on your IB exam. Woohoo! Here's a few more package problems. You guys hammer these out. I bet we can do these in about 5 minutes, and then we'll do a lab. Okay? All right, there's number 2. See what we can do with number 3. So a couple things to notice about this last problem, you guys. It says you have an electrical appliance that's rated at 2.5 kilowatts at 240 volts. IB will ask you questions about this. Things are rated as for a certain voltage. That's how much wattage they'll draw at a certain voltage. And then they'll throw in a question, what would this thing do if I plugged it into 120 volts instead? So kind of be thinking about that. So you'd use these numbers to figure out its resistance, right? And then assuming its resistance stays constant, you could then plug it into the new voltage and see what its power would be or something like that. Does that make sense? The other thing is that, power tells you how much energy is being used every second, and that's how you solve that last problem, is to figure out how much energy is being used in 2 hours worth of seconds.
Wait, how much?
All right, so here's where we started. Let's see what we covered. All right, looks like we covered a lot of the stuff.